We have an isolated charged conducting sphere. It's got a radius of 12 centimeters, creates an electric field of 4.9 times 10 to the 4 newtons per coulomb. At a distance of 21 centimeters from its center, what is the surface charge density? What is its capacitance? So given, I've got a charged sphere. And the radius of that charged sphere, I'll use capital R for that, is 0.12 meters. And I always try to make the unit conversion in what's given so I don't mess it up later, especially if it's easy. All right, we've got, but out here, and I'll say R equals 21 centimeters or 0.21 meters. And obviously, I'm not drawing this to scale, am I? We've got an electric field of 4.9 times 10 to the 4 newtons per coulomb. And that's what's given. So let's, what are we trying to find? For part A, we want the surface charge density, which we use sigma. And then for B, what is its capacitance? So we use the letter C for that. Solve. Well, what is sigma? That's the surface charge density. So for part A, sigma equals the charge over the area. So this tells me what to do. This tells me, hey, I need to find the charge. And I need to figure out what the area is of this sphere. And this is the charge on the sphere. This is the area of the sphere. Well, the area is equal to 4 pi r squared, because this is the area that's actually on this sphere right here. So one of the things that can happen, and I'll change this to capital R, right? Because I'm using capital R to represent that radius. There are two R's, and it's really common on these problems is to mess up your R's, get them confused. So just you got to really think as you go along. Now we want the charge on here. I'll do the work for that down here. We have an electric field out here, and one of the things that you have to recognize is that this charge that's here has a spherical symmetry to it. So the electric field lines just spread out in all directions. In three-dimensional space. And so as far as test charges out here outside the sphere, this looks just like a point charge. And so you can say that the E field is equal to KQ over R squared, and this R is this, I'm using little r to represent that, R squared. So I can solve this for the charge. The charge is equal to the electric field times R squared divided by K. Is that right? Did I do that right? Yes. Now, I can plug the numbers in and figure out what the charge is, or I can just plug this expression in there. I think I'll do that. ER squared over K. And now I'll just plug in values. We know that the electric field is 4.9 times 10 to the 4 newtons per coulomb. R squared, that's this one, is 0.21 meters squared, divided by K, which is 8.99 times 10 to the 9 Newton meter squared per coulomb squared, and then 4, and then pi, and then big R squared, capital R squared, and that's the 0.12 meters, and you need to square that as well. And you plug those values in. Let's check the units here. The meter squared cancels the meter squared. The coulombs cancels the coulombs squared. And let's see, we've got a meter squared on the bottom. The Newton cancels the Newton. and I have a coulomb. You know, if you reciprocate these units down here, you get a coulomb per meter squared, and that is indeed the correct units for charge density. So that's a good sign. When you plug all your values in with units, you check the units. If you get the right units, you've probably done it right. Probably. In this case, I did do it right. Right. So this should be 1.33 times 10 to the negative 6 coulombs. Microcoulombs per meter squared. And then for part B, the capacitance is equal to the charge Q over the voltage. Well, the voltage on the surface of a sphere. Now, what is voltage? That's how much work I got to go from, take a positive test charge from infinity and get it to that surface. Well, that surface is acting like a point charge up until you get to that surface. So you just use the voltage for a point charge. So let's use this expression again, E r squared over K. And what is this? This is K, oh, wait a minute. Oh, hold on a second. I was doing this the hard way because I don't need that. I can just go Q over, and this is K, Q over, now what R do I use here? Where am I? Where is the voltage? On the sphere itself. So I want to use R squared. And now that goes away, and I'm left with R squared over K. So that's going to be 0.12 meters squared over 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And when you plug all those values in, I think this is, hold on just a second. You get 13.3 picofarads, or I think it was 1.33 times 10 to the negative 11 farads. And, oh, this shouldn't be R squared. Whoops. I said it's KQ over R. That's R over K. And I did do this ahead of time. I just did it wrong right here. Okay. But yeah, and actually what I just did there, that mistake that I made using electric field instead of voltage, very common mistake. It's just an easy one to do. And I was looking at the units. I'm going, wait a minute, that Newton, Coulomb squared per Newton is not a farad. But but anyway, so remember that the voltage for a point charge is KQ over R, not KQ over R squared. That's the electric field. Okay. Sorry about that. Any questions? Okay. That is all.